Hello, I'm Hugh Manfield and welcome to my science channel. Now today I'm going to be talking about fluid space theory, MOND, and dark matter. Now what do all these theories have in common? Well, they all explain the galaxy rotation problem. Now a key difference though, while MOND and dark matter were created to explain the galaxy rotation problem, fluid space theory was developed as a visualization tool for general relativity. I was studying general relativity at the time and I couldn't picture what it was describing. So I began working on fluid space theory so I could get a mental picture of what's going on in a gravity field. And after working with that for a while, I began to realize that fluid space theory actually gives more than general relativity, a better, more complete description of gravity. And that more complete description of gravity describes the dark matter effect. So what is the galaxy rotation problem? Well, back in the 1930s, an astronomer named Fritz Zwicky was photographing galaxy clusters. And he discovered that the galaxies within these clusters were moving far faster than could be explained by Newton's laws and the amount of mass that was assumed to be in there. So he coined the phrase dark matter in German to describe some unseen matter that was increasing the velocity of the galaxies. Now the problem with galaxy clusters is when you take a picture, you get an image on a plane perpendicular to your line of sight. So you can get one component of the galaxy's motion, but the other components are unknown. So really he couldn't put a very good number on the amount of velocity in excess of Newton that there was. Now, later on in the 40s and 50s, Vera Rubin began studying the rotation curves of galaxies. Now, a spiral galaxy is a good candidate because it exists on a plane. And even if that plane isn't perpendicular to your line of sight with a telescope, you can figure out what that angle is, and then you can make a calculation and come up with a pretty good number for the orbital velocity of the stars within that galaxy. And that's what she did, and she began plotting these rotation curves, and she discovered that rather than dropping off as you would expect, the blue curve is the Newtonian form that you would expect. She saw much higher velocities that remained flat for great distances. And this began the search for dark matter. Now, these two were really pioneers in dark matter, and they did it the hard way, the old way. No computers, no calculators. They had to take photographic plates, chemical photography. To do what they did, you had to be a master of all trades. And my hat's off to their skill and expertise in actually being able to come up with usable data. It really is an art, and they had to be good at all aspects of it. Here is a typical galaxy rotation curve. And you see the dotted line represents what we'd expect from Newton's law and the amount of matter that we assume to be in the galaxy. And what we actually observe is this higher curve, like Vera Rubin discovered, that goes on at much higher velocities, flat out to great distances. And the difference between the observed and the expected is what is called the dark matter contribution. And it takes this parabolic form and is pretty much always in this form. This has led to the search for the elusive dark matter particle, but so far a particle of dark matter has never been detected. So how does dark matter work? Well, it's assumed that there's some sort of undiscovered exotic particle, and it tends to cluster around galaxies. It gets captured by the gravity field of the galaxies, and it manifests in a spherical halo. And this particle interacts only via gravity, and the presence of the dark matter increases the amount of gravity, increases the acceleration within the galaxy, and flattens the galaxy rotation curve. Now, one thing about this spherical halo is it's taken a lot of explanation as to why the dark matter particles don't get pulled down into the disk of the galaxy. And a lot of work has been done in that. But to me, the spherical halo is a big flag saying you're dealing with a field gravity fields project spherically. So MOND and fluid space theory automatically show a spherical halo. No more explanation is required. So they win the argument on the simplicity case in that respect. What about MOND? Well, back in the 80s, Monty Milgram proposed that there's something we haven't learned about gravity. Now, he had a hunch that this was the case and how it would work. And that hunch turned out to be very good. Fluid space theory has revealed that, yes, there is a lot that Einstein didn't include, and we have to go beyond Einstein to get a full understanding of gravity. So in that regard, he was right. And his proposal was that at some threshold acceleration, and this would be a low level, so this might be a galaxy curve in parsecs. So at some distance beyond the galactic core, you reach a threshold level and you transition, you modify Newtonian dynamics from an inverse distance square relationship to an inverse distance relationship. So the combination of these curves gives you an increased amount of gravity at long range that flattens the galaxy rotation curve. And this works very well. And it also happens to match the same thing that fluid space theory does. Only fluid space theory has a basis in theory rather than empirically saying, well, this is what makes the math work, so this is my hunch as to what's going on. So remember this chart. It's important later on in the discussion. Fluid space theory was developed to picture what's going on in a gravity field. And you do that by imagining space as a superfluid that's flowing down a funnel. Basically, it's spherical inflow, but you can take a slice out of that sphere, a cone-shaped section, and imagine it as a funnel flow. As the fluid flows down the funnel, it increases in velocity and becomes length contracted. And you get a length contraction field within the gravity field that changes the straight funnel into a hyperbolic funnel. And this contraction field will cause a small inward drift. All of these theories basically alter the acceleration of gravity. Fluid space theory does it by applying a scale factor to the acceleration. MOND does it by making a transition from the inverse distance squared relationship to an inverse distance relationship. And dark matter increases the acceleration of gravity by adding more matter. So you get a larger acceleration. So how you calculate the contraction field in fluid space theory is you start with the proper flow. Full uncontracted volume is flowing through a spherical surface, but it's flowing at escape velocity. So you apply the Lorentz transformation for that velocity, and you can calculate the amount of length contraction. And that's what I would call the observed flow. So then the difference between the proper flow and the observed flow is the amount of contraction. And that gives you a number for the amount of space that's being contracted as a function of the radius. You get what I call the drift velocity curve. And that's the amount that an object will be drifted inward by the contraction of space-time in a gravitational field. And it has a similar shape to the acceleration field. Here I have both the acceleration field and the contraction field contributions plotted on the same chart. And it's actually hard to do. The contraction field is much, much smaller than the acceleration field, and it gets dwarfed at short radiuses. But as you continue outward, the two curves converge, and just as with MOND, at some distant radius, the two curves will cross, and the contraction field will become more dominant than the acceleration field. So if you want to do the math, here's the equation for the drift velocity. And the way I did this is I used Newton's method of equivalent triangles, the same method he used to work out the orbit of the moon and work out his inverse distance squared law. Basically, it says if you have an object in orbit around a mass, over any given time, it will drop vertically some distance toward the central mass. If it's in an orbit, during the time that it drops that small distance, it has to translate horizontally to point B to remain on the circular orbit. And then he could work out the relationship between S and X and A and B and come up with an equation for the orbital velocity. Well, what fluid space theory does is it says, okay, you will get that same displacement due to gravity, but you'll get an additional displacement due to the contraction field. And you add those two together, and that will give you a higher orbital velocity. So you can combine these to create a dimensionless scale factor that will be equal to 1 or greater, and you apply that to the acceleration. Now I have plus or minus in the equation because fluid space theory also includes an expansion field, which would give you the minus case. But today we're only looking at the contraction field, the positive case, and the scale factor remains equal to 1 or greater. So when you plot the scale factors, an interesting thing becomes apparent. I started calculating the scale factor for small bodies like the Earth or Jupiter. Actually, I tried to calculate the scale factor for a hydrogen atom because I wanted to see what the contraction field of a hydrogen cloud would look like. Well, it turns out when I tried to calculate the scale factor, the number blew up because there's no point at which the two lines cross. It takes a lot of mass to get to the point where the acceleration field begins to drop below the contraction field. And the more mass there is, the closer that crossing point moves in, the shorter the distance it takes to get to that crossing point. So this is an interesting effect. And what it does is you see that the Earth and Jupiter out to 20 AU will project no extra gravity halo, no contraction field or dark matter effect. And the Sun out at 20 AU will have a very small effect. In fact, these numbers may be a little bit big, and the distances may actually be greater than shown on this chart. It's an old chart. But it illustrates the point that to get an effective scale factor, you have to have a large central mass. And the larger that central mass, the larger the scale factor becomes. So here's a chart, 4 stars from 1 solar mass up to 100. And I calculated when the scale factor would equal 2. That's when the displacement from the contraction field is equal to the displacement from gravity, and the scale factor is 1 plus 1, or 2. So to get a scale factor of 2 for the Sun, you have to be out at some 350, close to 400 AU, which is way out there. But for a 10 solar mass star, you only have to have about 50 AU. As the star gets bigger, the crossing point, the point where the scale factor equals 2, becomes closer and closer and closer in toward the star. This is a long range chart that shows in parsecs the effective scale factor for bodies of 10 solar masses up to 1,000,000 solar masses. So as you can see, even up to 1,000 solar masses, out at 20 parsecs, you get a pretty flat scale factor. You don't get a big dark matter effect or extra gravity halo. Only when you get up into 100,000 or 1,000,000 solar masses like the central black hole do you get an effective scale factor, which means that the central black holes of galaxies are going to have a strong correlation with the amount of extra gravity halo or the dark matter effect. Now this is going to be tempered because the large stars of 100 solar masses or more, or even 10 solar masses, if there's a lot of them and they're concentrated in the galactic core, collectively they can create a dark matter scale factor that's on par with the black hole. So the dark matter halos or the extra gravity halos are going to be really dependent on the size of the black hole and the composition of the galactic core. and the rest of the galaxy and the small bodies are going to contribute very little to the dark matter effect. And another thing about these charts, these scale factors, while the chart ends, if you plotted this out farther and farther, it would continue to follow the same parabolic curve, increasing with distance, which means that there's no end to the dark matter effect. Galaxy rotation curves, predicted by fluid space theory, should go on indefinitely and be flat indefinitely. And that's just what's been recently discovered in a study by Case Western Reserve. They studied the long-range rotation curves, and they discovered that galaxy rotation curves stay flat well beyond the rim of the galaxy. The galaxy ends basically at these red points, and the rotation curves of objects that would be in orbit around that galaxy would remain flat almost apparently indefinitely, which supports fluid space theory and actually supports MOND and is a strike against dark matter, because it was always assumed that the dark matter halos had to taper off. And if they don't taper off, then there's a lot more dark matter. And how's that going to affect everything? It really throws a wrench into the dark matter works. Another test for dark matter is the bullet cluster. Now, what you have in the bullet cluster is you have a cluster of galaxies, basically here in this blue area, and you have another cluster in this other blue area. And these two clusters passed through each other some time ago. And what happened is that as they passed through each other, all the gas and dust clouds that were in those clusters collided and remained in the space between as the clusters went through and then away from each other. And what you see in this image is shaded red, the location of the gas and dust clouds, and in blue, due to gravitational lensing, the dark matter halos associated with these clusters. And this has been said to support dark matter because with MOND, you take all of the gravity of all the bodies, and that would tend to tell you that the dark matter should be displaced a little bit more in where these gas and dust clouds are. But what fluid space theory says is no, gas and dust clouds don't project a dark matter effect. They don't project an extra gravity halo, and the extra gravity halos are basically projected from the black holes and the galactic cores, and the dark matter lensing is right where you would expect it to be. So this is another way that MOND could be improved, because there's no way that MADI could have realized back in the 80s that only the galactic cores contribute to the dark matter effect and that the small bodies don't. And that had to be learned by going beyond Einstein with fluid space theory. So fluid space theory offers some pointers that can improve the effectiveness of MOND. There are other interesting galaxies out there. There are ultra diffuse galaxies, which either seem to be 99% dark matter or have no dark matter at all. And what this would tell us is that either they have a black hole or they don't. That's what fluid space theory would tell you. If they don't have a black hole, they're going to obey Newton's laws because there's no central core that's projecting an extra gravity halo. But if they do have a black hole, that black hole is going to project the contraction field, and that's going to dominate the rotation curve of the galaxy, and you'll get an all dark matter type galaxy. So in conclusion, Marty Milgram was right back in the 80s when he said there's more we need to learn about gravity. And fluid space theory goes beyond Einstein and tells us many things more about gravity than just the dark matter effect. So please watch my other videos. I go into a lot of these different aspects in the other videos. And the first 10 in my video series could really be considered Fluid Space 101. So if you watch those first 10 videos in order, I lay out the case for fluid space theory in a logical, orderly fashion. Fluid space theory is the right theory at the right time. and it has been for years. Until next time, I'm Hugh Manfield.